Here our differential equation is y prime equals y plus 1 times y plus 2 times y plus 3. So then our equilibrium solutions are at y equals -1, -2, and -3. So for this one, let's go ahead and start by evaluating the stability with partial f partial y everywhere. So the first thing, right, f of y, right, y prime equals f of y, is just the right-hand side of the differential equation again, so y plus 1 times y plus 2 times y plus 3. If you do multiply that out, you end up with y cubed plus 6y squared plus 11y plus 6. Right, and then if you take the partial derivative of f with respect to y, you'll end up with 3y squared plus 12y plus 11. And I'm going to avoid all the calculations here. It's not worth the effort. I just pre-computed them. So partial f partial y evaluated at y equal to -1. That ends up being +2. +2 is greater than 0. So that means that this is unstable. All right. And then partial f partial y evaluated at y equal to -2. That ends up being -1. That's less than 0. So this ends up being stable. And then I've got partial f partial y evaluated at y equal to -3. Well, that ends up being +2. And that is greater than 0, so that ends up being unstable. And if we go back, we look at the graph here of the direction field, that does seem to be agreeing. So according to what we have over here, we should have -1 is unstable, -2 is stable, -3 unstable, and that does appear to be the case. So this is unstable, this one's stable, and this one's unstable. Right, drawing in these trajectories, they'll do something like that, something like that, something like that, and something like that. And we can actually use these as well to draw what the phase line graph would kind of look like. So if we pick our points here at, let's say, -1, -2, -3, we know that partial f partial y has a positive slope at -1. So that means it has to pass through something like that at y equal to -1. At y equal to -2, the partial f partial y is negative, so it has to pass through something like that at y equals -2, and then again it's positive at y equals -3, so that means it has to have a positive slope there. That'll be y equals -3, and then we can kind of connect the lines together to make them work. So this one's going to continue going down, this one's going to come up and join y equals -2, negative. This one has to come and join the y equals -1, and then this one should just go up forever and ever and ever. Then using that, right, we have our arrows, so the arrows on this side will be increasing, arrows on this side, since y prime is negative, decreasing, getting a little bigger until you get to the greatest negative value, and then getting smaller again. This one positive, so that one is increasing that way, bigger in the middle, and this one is going away. And right, based on those arrows, based on the slopes, this one's going to be unstable, this one's going to be unstable, and this one's going to be stable. Another thing you can check on this is the stability of the fixed points will flip. So I can't have a stable one adjacent to a stable one. It always has to flip. So it goes unstable, stable, unstable. And also with kind of semi-stable, the halves of the semi-stable, it'll have to follow this flipping behavior where it alternates between stable and unstable between adjacent fixed points.